Hello, this is Mr. P, and today we're going to talk about transformations. We're going to use transformations to be able to quickly and easily graph all of our different parent functions and all of our different functions. As long as you know the properties and the shapes and the characteristics of the parent functions, then by using these transformations you can really graph any version of that type of function. One thing about this chart here is you might see the word outside and inside. What we mean by that is that's inside or outside of what the function is mainly doing. So if we have y equals the absolute value of x, for example, then inside would mean we're adding or subtracting. Inside means we're doing it inside of that absolute value sign. If what the main thing is, the function is doing is squaring, then if you have a parentheses raised to that square, then anything you do inside the parentheses is what we mean by inside. And then any multiplication, addition, subtraction done outside the parentheses, that's what we mean by outside. And you're going to find that anything done to the outside of the parent function is going to be intuitive. It's going to affect the graph in the way that you would think it's going to affect the graph. And inside, for most people, tends to be counterintuitive. All outside changes have to do with y values. So they will be vertical changes and they will affect the y values in your graph. And any changes you make to the inside of the parent function are going to be horizontal changes and they will affect the x values of your graph. So here, if we add something to our function, then outside is a vertical change, so it's going to go up or down, and it's just what you would think. Adding goes up and subtraction goes down. So sticking with the outside, if we multiply or divide, you would think multiplying makes something bigger, and it does. Multiply is going to stretch your graph vertically, and dividing by a number outside of the parent function will compress your graph vertically. If you change the signs or multiply through by a -1, then that is going to have the effect of reflecting your graph. And if you reflect it about the x-axis, that would be the same as a vertical reflection. Remember, all outside changes are vertical. And if you, of course, reflect it horizontally, that would be changing the inside. That would be multiplying the inside by a negative number. And speaking of the other insides, the up or down becomes left or right when you're talking about inside, because those are horizontal changes. And you would sort of expect intuitively that addition would make it shift to the right, but this is the counterintuitive case. It actually shifts it to the left if you add inside the parent function. Subtracting inside the parent function will shift it to the right, and then you would normally expect, like you did in the last case, that multiplying makes the graph bigger. But instead, if you multiply inside the parent function, you're going to compress your graph horizontally. And likewise, dividing is going to stretch your graph horizontally. So a lot of these will become more familiar with examples. We first need to know what our parent functions are. We have to have a good handle on the properties and the shapes of these parent functions. So the main ones we're going to look at would be these functions. And for the first one here, notice how this function stays at the same value. Remember, the height of the function is the value of the function. So this value does remain constant. That value doesn't change. No matter what the input is, the output is the same value. So that can be expressed, or the name of that, of course, is a constant function, because that value is remaining constant. And that can be expressed with an equation such as y equals c, where c stands for some constant, some number. So y equals 5, y equals 2, y equals 3, or here y equals, looks like 5 halves. That would be our constant function. The next one is a line. It's a linear function. This is a special one of the linear functions. It's in the group of linear functions. But this one in particular goes through the origin, and then it goes through 1, 1, 2, 2, 3, 3, 4, 4. And the equation of this would be y equals x. And that is a special type of linear function called the identity function. So it's the identity function or it's the linear function. They are one and the same. Now for the absolute value function, we get a graph that looks like a V. When you have x is positive, then y is going to be positive. But when x is negative, y is also going to be positive. That's how we get that shape. So like I said, that's called the absolute value function. This acts as a vertex. That vertex is at the origin with the parent function. And of course, the equation would be y equals absolute value of x. For the parabola, you might recognize this as a parabola. So our equation would be y equals x squared. And that is called a quadratic function, or it's also known as the squared function, because it's x squared. So quadratic function, squared function, parabolic function, they all refer to this graph, which we will talk a lot more about the shape in a moment. This graph here is a cubic function. The name of that one is a cubic function, and that would be y equals x cubed. Because notice how when you cube a negative number, it's still going to be a negative number. When you cube a positive number, it's going to be a positive number. And then this one here, the shape of this, if you take this and think of it in this direction, and look at just the positive branch, ignore the negative branch, then the shape here and the shape here would be the same. The nature of those two curves are the same. That's because this one is a square root function. So the square root function, of course, is going to have the equation y equals square root of x, and we just ignore that negative branch. And the graph will start here. The domain is from 0 to infinity. So the graph starts here and goes on forever in this direction. For all the other graphs so far, by the way, the domain has been all real numbers. For the square root function, the domain is all non-negative numbers. So it's 0 to infinity, including the lower bound. And then finally we have the cube root function, would look like this. It's basically this one reflected about the line y equals x. This is this graph reflected about the line y equals x, but then we ignore the negative branch because you can't take the square root of a negative number and have it result in a real number. So with the cube root function, again, you take the cubic function reflected about the line y equals x, and you get this shape here. Now, I do want to say something real quick about the intuitive versus counterintuitive. You notice here we were saying this is the intuitive case and this is the counterintuitive case. Well, if something's counterintuitive, then really it just means your intuition needs to be recalibrated. So I'm going to show you something that if it confuses you too much, don't worry about it. But if you really want to know why we shift to the left when we add inside, then I will show you here. Let's take our parent function of y equals x squared. And we should know that the shape of this, by the way, if we have our vertexes at the origin, then we will have a point at the origin. We will also have a point at 1, 1 and a point at 2, 4. That's because 1 squared is 1, 2 squared is 4. For every change in horizontal distance from the origin, every horizontal change will result in the square of that being the vertical change. So that's the relation that this function graphs. And there's going to be symmetry. The branch going off to the right from the origin is the same as the one going off to the left. So if I go left 1, I go up 1. If I go left 2, I go up 4. Knowing that basic shape is going to help you graph quadratics a lot quicker. Again, it's from the origin. It's 1, 1 and 2, 4. On both sides. Okay, with that being said, so if we were to add outside the parent function, for example, let's say we have y equals x squared would be this. Y equals x squared plus 3 would be this. We simply take the entire graph and shift it 3 units up. This would be the graph of y equals x squared plus 3. By doing that, though, the shift does not change the shape at all. From the origin, it's still 1, 1, and it's still 2, 4. Same with the other side, 1, 1, 2, 4. That way, if you know where the vertex is and you know where the shape is, then you can make those 5 points and draw your parabola. Now, if instead of x squared plus 3, we had x squared minus 3, well, then that would be this graph. So we have from the origin again, 1, 1, 2, 4, which puts that point. It does not change the shape. So shifting up, down, left, right doesn't change the shape. When you multiply or divide, that's going to change the shape of the graph. So here, if we add or subtract inside the parent function, then technically we're not shifting the graph, we're shifting the plane. And this is why it's the opposite of what you would think it is. So inside the parent function, we're affecting the input value, so we're really shifting the plane. So if I add 2 inside, so let's say it's y equals open parenthesis x plus 2 close parenthesis comma squared, or not comma, squared, all squared, then I'm adding 2 inside, which means the graph is going to shift 2 units to the left. But in reality, what's happening is we're shifting the plane 2 units to the right. Notice how that has the effect of the graph shifting 2 units to the left. Now, if that confuses you to think about it that way, then no problem. You can go right back to just shifting the graph itself left to right. But shifting the graph 2 units left is the same thing as shifting the plane 2 units to the right. Alright, so let's look how we can graph something using our newfound knowledge. We're going to graph this equation right here. It's y equals -2 times the quantity x minus 3 quantity squared, and then plus 4. And we're going to go through all the different transformations. We're going to go through them one at a time. Notice how we have a negative sign out in front. We have a multiplication happening outside the parent function. We have subtraction happening inside the parent function, and then we have addition outside the parent function. So we're going to start with the graph of the parent function, which is just y equals x squared. We recognize that's the family that this graph comes from. So here we have from the vertex, which is at the origin, 1, 1 is another point, and 2, 4 are points on the graph. And it has left-right symmetry, so 1, 1, 2, 4 in the other side as well. Now we can take the transformations in any order, but I'm just going to take them from left to right basically. So we're first going to look at the negative sign. The effect of changing y equals x squared to y equals negative x squared would mean a reflection about the x-axis. So we're going to flip it vertically about that x-axis, or in other words, instead of opening up, it's going to open downward. But notice how this shape is still 1, 1, 2, 4. We still keep that same shape. Now, if I multiply by 2 outside, in other words, if instead of negative x squared I have -2 x squared, then that is going to stretch the graph vertically, which means it's going to affect the vertical or y distances. So instead of 1, 1, I'm going to go 1 and then twice as much as what I had before. It's going to be 1, 2. And instead of 2, 4, I'm doubling the y value only, so it'll be 2, 8. So when I do that stretch, the graph is going to look like this. From the origin, instead of 1, 1, I go 1, 2. And then instead of 2, 4, I go 2, 8. And we're talking about 8 units away from where you are. So we're talking about distances here. Alright, so that's the effect of multiplying outside. It stretches the graph vertically, which does change the shape. The first reflection did not change the shape. Second one did change the shape. Now we're going to look at the -3. So we're going to subtract 3 inside. That means I'm replacing x with the quantity x minus 3. And since it's inside, it's the counterintuitive case. So instead of negative meaning to the left, it's really going to be to the right. So I'm simply shifting the graph that we had, which was the red one. I'm shifting it 3 units to the right, but keeping the same shape. So if you want to do it by matching out point for point, the vertex, which was at the origin, is now 1, 2, 3 units to the right of it. And then notice how the shape stays the same. It's 1, 2, and 2, 8 is the shape of this now that we have the 2 in the front. And then the final transformation is to add 4 on the outside, and adding 4 would just mean shifting it up. And when I do that, we go up to the final answer, which is our green graph. The vertex went up 1, 2, 3, 4 units, but then by shifting, we do not change the shape, so it's still 1, 2, and still 2, 4 for that standard shape, or for that shape. Now, when you actually graph these, though, you don't have to show all these intermediate graphs. I wanted to show you so you could see that we can do these one at a time and what each transformation means, but let's look at a more realistic way that we would have done this problem. Because when you get proficient at this, you can basically look at this equation and be able to go right to the graph. So here I'm looking at, and it's going to be green, I'm looking at although you can do them in any order, I believe a good way to graph parabolas is to first find the vertex and then determine the shape and whether it opens up or down. So my vertex is going to be the value of x that causes this to be 0, causes the inside to be 0. That will be the x value of the new vertex. That will be the shift. So here, instead of we first recognize this as y equals x squared. That's our parent function. And instead of this vertex being at the origin, it's going to be, for an x value, the value of x that causes this to be 0. Well, if x is 3, then the inside is 0. If you can't see that right away, then you simply take whatever the expression is on the inside and set it equal to 0. You have x minus 3 equals 0 and solve that equation algebraically. So if x is 3, the inside would be 0, so 3 is the x value of my vertex. And then the plus 4, the adding anything on the outside, is simply going to move the graph up 4 units, so that vertex, instead of being at the origin, the first shift here moves it 3 units to the right, and then the next shift here moves it 4 units up, which means my vertex is going to be right there. So I can put my point there and that determines where my vertex is. Next, I would look at, am I opening upwards or am I opening downwards? And the negative sign means I'm going to open downwards. And then the 2 is going to tell me the shape. Instead of the standard shape, which is 1, 1, 2, 4, 2, 4, which is what it would be if there was no number here or if it was a 1, it's going to be double in all of the vertical distances. So instead of 1, 1, I go 1, 2, which means we're going to put a dot there. And likewise on the other side. And then instead of 2, 4, I'm going to go 2 and then 8 units puts me there. And then 2, 8. So with those 5 dots, I can plot those just by looking at the equation and knowing what to look for. I can go right to those 5 dots, and once I have those 5 dots, I can draw a nice smooth curve through them, and that is your correct graph. That would be the correct way to think your way through that problem. Alright, with transformations, it's going to be much easier if you think of these graphs all as being the same parent function, and then just realize that there are little adjustments or transformations from that parent function. Then it'll be much easier to graph these. And we're done.